come once again to this discussion on very fundamental issues about optimization. Now we learnt about what is the descent direction and in the last lecture, and we found that if this sort of condition, this criteria, this grad fx bar into d is strictly less than 0, and this d becomes a descent direction. So for us to find the direction of descent, we have to find a d, small d, such that at some x tilde where grad fx bar tilde is not equal to 0. We have to remember that in our setup grad fx bar is not equal to the function f is assumed to be differentiable, not only differentiable, we can even assume it to be continuously differentiable. So for all purposes I again want to state that f will be assumed to be continuously differentiable. Means not only the function is differentiable, all the partial derivatives that you have of this function, they are also differentiable as functions of x1 x2 dot 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 xn. Now let us give some examples of directions of descent. Suppose I choose d is equal to minus grad f at x hat. So then if grad f of x hat is not 0, then putting this, so grad f x bar d is now this. So this is equal to minus of grad f of x hat into grad f of x hat, not into inner product. This is nothing but norm of norm, you know, is a positive quantity in this case because grad f x bar is not equal to 0. So this is strictly less than 0. So this direction d is called the direction of steep. We will come very soon in the to study the problem of solving an optimization problem, unconstant optimization problem by using the method of steepest descent, but for the moment just know that it is called the method of steepest descent, and we will actually explain why it is called the method of steepest descent or the direction of steepest descent. Another one could be like this. For example, if you take d to be minus b time, where b is symmetric and positive definite. Where d is symmetric and positive definite. So let us see what would happen with grad f x tilde into d. Now you see this vector d, which is the direction of steepest descent, d cannot be equal to 0 because if d is equal to 0 it cannot be a direction of steepest descent, and we do not want 0 vectors because we actually some point where you know the optima is not achieved or local minimum is even not achieved, then you want to move away from that point, you want to move to a point where the function value decreases and sufficiently decreases. So and you move a certain distance away from the point. So if you put d equal to 0, then of course that has no meaning. So in this particular case we will have nothing but now grad of fx tilde is not equal to 0, that is a basic assumption, but b being positive definite, this would mean that this whole thing is strictly less than 0, because this part is strictly greater than 0, this part, and so this is strictly less than 0. So this is also a direction of descent. One of the important directions of descent is to have something like this at fx bar. Take the Hessian matrix we have already known what a Hessian matrix is. So in place of B I have put this matrix. So here this is a particular case with B equal to the inverse of the Hessian matrix. Now this is B is positive symmetric definite, so we had this, but if say the Hessian matrix itself is positive semi definite at x hat, then B itself is also the inverse is also positive semi definite. So when D is taken in this way, this is called the Newton iteration. And Newton iteration would lead to Newton's method, which is a very important class of methods which we will study in detail. Okay. So we have this very basic starting information. Now see what we can do. So now what we know is that if this is my xk at the present moment, so xk is the current iterate, so is the kth iteration, and you know the grad of fxk is not equal to 0, and suppose this is my direction of descent, suppose. So I want to move from xk in this direction, so I move a distance, I come to a point xk plus some alpha k dk, and what I want to have is that at that point f of xk plus alpha k, or you can say this is dk, that is a descent direction chosen for xk to move from xk. This one must be strictly less than. So now you once you know the descent direction, it is fine, but how you cannot move very little from xk, then your movement is not very good. Even if your function value decreases, you have not moved away quite a good distance, because if you do not move away quite a good distance, then you are not improving your algorithm, you are not going quite faster towards the minimum. The goal of optimization algorithms is to make you start from a starting point and reach the optimum solution as fast as possible, but that has not been possible here. So maybe I will use a chalk for a while and see what happens here is the following. Now here you have the xk and your actual optima is here, your x bar. So now here you have a descent direction. Now here you are moving in the direction dk, if you move then your function value decreases, but you cannot move for a long while, because you know that there is a threshold alpha naught beyond which all this is possible. Now you have to move as far as possible from xk, because then you will have this new point xk plus alpha k dk. So this new point you have to move in such a way so that my function value decreases as much as possible, because I want to minimize, because from here the new point, say you need to go to some direction, maybe it is decreasing in this direction, from there you need to go to this direction and so on, maybe it will come to this direction and this direction. So now what we are essentially doing, so we are moving along a line and then searching how much we have to move along that direction dk. So this would be, so we will decrease the function value. Our objective here is of course that you should have but if I move alpha k very less, if I come here then my decrease is also very less. I am making a very less decrease which is not very good. So the idea is that you cannot make such a small decrease, you cannot just come here. So you have to make a sufficient decrease. So how much is that sufficient decrease would be the question. Now what is this alpha k? This alpha k is called the step length at k. And this alpha k, to the step length at k, this plays a fundamentally a crucial role. Okay. So this is something you need to take care. Here we can call alpha k Now the question is how to determine the step length. So whatever be your descent direction, it does not matter, our point of concern would be how to determine the step length, and for that I would again go and do certain explanations in the board. So what you have here is this function phi alpha. So once I know my xk, so for a fixed given k, kth iteration, so I have actually fixed my so this xk and your dk, these are now fixed vectors. So now once these are fixed vectors, let me construct this function phi alpha. Now you see this is the function value of f along this line, points on this line. Alpha could be any number strictly bigger than 0. Now I have to know to what extent I can keep on decreasing the value of f, because d is a descent direction. I know that there exists an alpha naught beyond which for every alpha this function value is strictly less than fxk, but to what extent I will get the maximum decrease. The natural thing is to find an alpha for which along this line, along the direction dk, this function value is minimized. Basically then I am basically trying to find or more specifically this is the same as writing now suppose I find a minimum of this problem, that is alpha k, then the function value at alpha k, at the so at the function value at alpha k, that is, so phi of alpha k is less than equal to phi alpha for all alpha greater than 0. Step length is always positive. So now what you see is that this this alpha k should be ideally my choice of step length. So alpha k is the ideal choice of step length. Okay. The question is, can we keep on doing this in practice? So, we have seen on the board as to what should be the ideal step length. The ideal step length would be to find the minimizer, but the question is that can we really go on doing that? That is, can we really find the ideal, can you really find the minimizer? So, you see here the problem becomes difficult. Difficult in the sense is that we want to minimize function phi alpha over alpha greater than equal to 0, where phi is a function from R or R plus to R. R plus is a set of all non-negative real numbers. Now, here this problem is a constrained optimization problem, because you have an additional constant that alpha is restricted to the non-negative part of R. So, it is a constant optimization problem. So, what we are having that, so we have a unconstrained problem in a higher dimension. So, an unconstrained problem in Rn needs the help of a constrained problem in R. So, this is a quite a important issue, but there are a lot of methods of how to solve such a problem by bisection method, this method, that method. So, but we are not going to get into the details of this. So, the trick here is the following. The question is how to determine the step length, but the more important question would be how to determine the step length in an inexact fashion. That is, you did not find the exact alpha which minimizes this problem, but you can find an alpha which makes a sufficient decrease. So, what is this sufficient decrease called? So, let us define what we would like to mean by sufficient decrease. What we are doing now is essentially the fundamentals of line search method. So, we are going to write down something that what we are doing here, our thing is called line search method. There is something called trust region methods will come later on. Now, what do you mean by the sufficient decrease? So, what should be the alpha? So, choose an alpha greater than 0 such that f of x k plus alpha times dk is less than equal to f of x k plus c1 times alpha times grad of f of x k into dk, where dk is the steepest direction. Dk is the not the steep, sorry, dk is the direction of descent. So, let us remove this little part here, because we have already started this inexact business. So, let us see what does this statement means, the sufficient decrease condition actually means. So, now of course, you have to choose C1. Where is C1 from? C1 some number chosen between 0 and 1, excluding 0 and 1. So, what we have done is the following. So, you have to find an alpha such that f of x k now because decay is the direction of descent, we have needs to be strictly less than 0, but alpha is strictly bigger than 0, C1 is strictly bigger than 0. So, this would imply that for such an alpha, if would imply that for such an alpha, this is a negative quantity. So, f of x k plus a negative quantity is obviously strictly less than f of x k, this is a strictly negative quantity. So, f of x k plus alpha so because this part becomes completely negative. You see the interesting part is this, that we are not only expecting this to be true, but we are expecting that this is lesser than some quantity which is quite less than this quantity. Essentially what we have done is that we want to have x k an alpha which has this property. So, f of x, so this if we can find such an alpha, if we find such an alpha, we put alpha is equal to alpha k, we can now put x k plus 1 is equal to x k, that is the k plus 1th iteration value, that is this is my k plus 1th chosen point, it could be a solution, could not be a solution, alpha k dk. So, what we have done, if you can find such an alpha here, then we put x of k plus 1 is x k plus alpha times dk. So, this is what is called the line search iteration criteria, or this is called the line search this direction of steepest descent, it is sometimes called the Armizo condition. This is called the Armizo, this condition, this steepest, this sort of condition, this is called the Armizo condition. Now there has been a issue which comes up here, is that even if you choose C1 which is a fraction of this thing, even to get this alpha could be very small, this alpha will have to be very small. But if this alpha is becoming very small, then you have not made much movement from x k. If alpha is very small, then you are here, then actually possibly you should be here, for which you have the actual alpha which minimizes the function phi alpha. So, the whole thing is that then how do you stop such short step lengths? If you have a very short step length, then you do not make much progress from x k, and that is not desired when you run an optimization algorithm. So, the question is how to avoid short step lengths. To avoid short step lengths, you have to consider another criteria called the curvature condition. So, we have to now consider what is called the curvature condition. Okay. So, what does the curvature condition tells us? Curvature condition tells us find an alpha such that you would have this. So, such that the gradient at f of x k plus 1 basically see what happens is the following. Let us try to understand the sufficient decrease condition or Hermizzo condition in a more geometric fashion. So, let us use this diagram here, we will just make certain changes. So, let us try to understand this in a better way. So, let us consider this part as alpha and this is my phi alpha. When alpha is 0, then it is f of x k basically. So, phi alpha is f of x k, some value here. Now, as alpha is changing, this is say phi alpha, this is say the graph of phi alpha. This is the graph of phi alpha. Now, what happens? Look at this expression here. Let me call this as L alpha, and let me write L alpha is f of x k plus C1 times alpha into grad f x k dk. Now, at alpha equal to 0, this is f of x k, this is your f of x k. Now, let me take the derivative of L alpha or the direct. So, the slope of the line L alpha. So, L alpha given an alpha, this is y equal to mx plus c form. So, L alpha is a straight line, but how is its slope, in which direction it is moving. So, its slope L alpha, the direction f dash x at alpha is nothing but C1 into grad f x k dk. So, it is strictly less than 0. So, now L alpha is some line like this. So, this is my L alpha. I am going to accept that alpha for which this value or phi of alpha. So, what I want to accept alpha. So, my idea is simple, accept alpha if phi of alpha is less than L of alpha. So, you see there is a negative slope, the angle at which it will hit the x axis is obtuse. So, let us see what happens here is that you see here phi of alpha is bigger than L alpha. So, I do not accept that alpha, here it is less. So, this is the acceptable zone, accept alpha. So, these alphas are acceptable, but these alphas are not, these alpha is again acceptable, while this is not, again this alpha is acceptable, right. So, this is accept. you need not move away so much, right. Maybe it is usually something like this or like this something. I am just changing the drawing a bit because okay, you cannot have all alphas acceptable. So, you see that, so these are the regions of acceptance. So, these are the alphas you would accept as your choice, but once you have this curvature, but now here you see there is no problem, but it could be slightly problematic if we had this. Now, let me change the diagram a little bit and let me look into this situation. If I look into this situation where you have say phi alpha in this fashion, so this is my phi alpha and this is alpha. So, this is my L alpha. So, you see this is my acceptable zone, this is accept zone, accept alpha zone. So, this is my accept alpha. Now, here I could choose an alpha which is very, very small. So, I have not moved sufficiently off from xk. So, in order to avoid that, I need to have the curvature condition which tells me that too much short step lengths cannot be taken, which condition is nothing but as we have written in the other format, we need to find an alpha which, now you are asking something to be bigger. Now, this quantity is negative where C2 is of course taken between C1 and 1, this quantity is negative, but this quantity could be positive also, or this quantity could be 0 also, or this quantity could be negative also. Of course, positive would not give me any information, then decay would not be the descent direction at of course, it could be positive because there is no guarantee that decay is a descent direction at xk this point. So, this is called the curvature condition which we have written down. So, this is to avoid too short lengths. So, sometimes in algorithms people use the Armizo condition in comparison in jointly with the curvature condition. So, what I want to say is the following, that you can combine these two conditions, but there has been a result by the famous optimization theorist Wolfe. This is sometimes when you combine these two things, Armizo's condition with the curvature condition, it is called the weak Wolfe condition. So, you could also define the strong Wolfe condition, The strong Wolfe condition is Armizo plus this fact, that I want to have the alpha satisfying the Armizo plus also having the alpha satisfying not just this, so alpha has to satisfy both of the things. So, Armizo, this is called the strong Wolfe condition, and another is called Wolfe condition. This is Armizo plus this condition, that Now we will show that if we consider the Wolf condition, then there exists interval lengths, that is you can find intervals of alpha which satisfies both these conditions. Now under a very mild condition, that you will always find alpha. The very important thing is that if you are telling that I will take this condition and that condition, I want to find an alpha, before you really do the numerical algorithms, you need to really confirm that yes, I can actually go ahead and find an alpha. So how do we find that alpha? That yeah, we can guarantee that such an alpha which satisfies the Wolf condition or maybe the strong Wolf condition. We will not bother with the strong Wolf condition at all here. So my next question would be the following: can we find an alpha greater than 0 such that the strong, or sorry, the Wolf condition is satisfied? The Wolf's condition is satisfied. So tomorrow's lecture would begin with the study of this fact that okay, yes, I will show that under a very mild condition, which is nothing but which is assuming that the f is actually bounded below on this line, that is if f is bounded below on this line, if you take xk and here is again your line, this is the ray xk plus alpha dk, where dk is the direction of descent, then if dk is the direction of descent, if along this line or along this ray there is alpha is strictly greater than 0, greater than or equal to, if the function f is bounded below on this, then you are always sure to find an alpha which will satisfy the Wolf condition or the strong Wolf condition. So this is this is a very important result. So it says that is what we are going to prove tomorrow. If f is bounded below, that is it has an infimum below on dk 0, then there exists alpha greater than 0 such that the Wolf condition holds. Okay, I am not written directly, that is okay. Wolf condition would holds with that is what happens. So this is what we will discuss tomorrow. First we will prove this fact. Once we have proven this fact, we would like to show how to use the Armizo condition, that is we do not use the Wolf condition. In real practice we can actually use the Armizo condition, and that is called the backtracking line search. So we will see how we can use the backtracking line search and go ahead and do the algorithm, and then we will really talk about a particular type of method called the steepest descent method. We will then talk about the convergence and the rate of convergence and all these fundamental issues related to algorithms. So when we run an algorithm, we have generated those iterates, but how do I assure that these iterates, this sequence of iterates would converge in the mathematical sense of convergence of a sequence to a point which is at least a critical point of the function, that is at least a point where grad of fxk is 0. More happily it would be if it goes to a point which is the minimum, but it does not go to a, we cannot guarantee that it will go to a minimum for just any function, but for certain types of function okay it does. So that is what we will do. So we will stop here today. Thank you very much.